Hello and welcome back. Today we're continuing on 7.3. So we're getting into the application portion of the section. So for this first application, we're going to look at an open top box. And it's also going to have two dividers. And some restrictions: it needs to hold 216 cubic inches. And we're going to find the dimensions to use the least amount of material. So I'm going to start this one with a sketch. So we have an open top box, and you've already seen other times this semester my drawing abilities have not made me into an art teacher. So open top box, so this part, the lid does not exist. This is open. We have the other 5 sides of the box, and we also have 2 dividers in the box. So we have our height, we have our width, and we have our length, and we're looking to optimize those dimensions where we want to use the least amount of material and still have our constraints met, where we need to get the 216 cubic inches of storage within this open top box and still have the 2 dividers. So what we know, the volume is 216, again in cubic inches. The volume of this cube will be just the product of length, width, and height. So by a little bit of substitution, length times width times height is 216. And we can isolate one of the variables. So I'll get, I just picked the length. Length is going to be 216 w to the negative first, h to the negative first. So dividing both sides by wh. So that's our constraint portion. What we're looking to optimize is the amount of material. So the amount of material used will be a surface area problem. So the bottom of the box is the width times the length. I have a left side and a right side, as well as 2 extra sides for my 2 dividers. So I have 4 sides that are each length times height, and a front and a back. I have 2 of those that are each width by height. So now we do a little bit of substitution. Instead of SA, I'm just going to shorten it to cap S for surface area. So cap S is width by 216 w to the negative first, h to the negative first, plus 4 times, there's our length again, dropping our 216 w to the negative first, h to the negative first, times h, plus 2 times w times h. So now we have something that's at least a little bit more manageable. It's one function with 2 input variables instead of 3. So a little bit of cleanup here. W times W to the negative first will cancel out. So we have 216 h to the negative first plus then 4 by 216, 864. W to the negative first and h to the negative first times h will cancel out. And we bring our 2wh along as well. So if we're looking to optimize, we're looking for a local min or a local max. So we're looking at partial derivatives. So partial with respect to w, that would have this first term drop off. Then we would have minus 864 w to the negative second. And here on the last term, 2 and h are treated as constants. W is the variable, so plus 2h. Now we also, I'll put a little box around that since we're going to be coming back to that. We'll do a partial derivative with respect to height as well. So now we have negative 216 h to the negative second. Middle term drops since there's no h's involved and we're differentiating with respect to variable h. And then our last term, now the 2 and the w are treated as if they are just numbers. So we have plus 2w. Derivative of h would be just a trivial 1. So we also want partial derivatives, or second partial derivatives. So we'll find SWW. A little recall I'll put at the top of the page there. Partial with respect to w was negative 864 w to the negative second plus 2 times h. So differentiating once again with respect to w, the term on the end will drop. Negative by a negative kicks us back over to a positive. So we have 1728 w to the negative third. With respect to one, then the other, we would have a 2. And a little reminder of what partial with respect to h looked like, negative 216 h to the negative second plus 2w. So you can see that that would still be the same. If we had flipped the w and h, we would still have a derivative of 2. And our partial with respect to h both times, negative by a negative kicks us back over to positive, so 432 h to the negative third. So if we have a local min or a local max, it's happening where our first derivatives are 0. So we set each one to 0 and we'll go ahead and solve. So our first derivative with respect to w will set to 0. 0 is negative 864 over w squared plus 2 times h. And our other first derivative will also set to 0. Negative 216 over h squared plus 2 times w. So this is really part of a system. As you can see, it's a nonlinear system, so substitution would be our easiest bet as far as solving it. So I'll solve this first guy for h. So 2h is worth 864 over w squared. So I move the 864 over w squared, then we cut both sides in half. So h is 432 over w squared. And then we'll substitute that into the second equation. So 0 is negative 216 over There's our h, and we have it squared, 432 over w squared plus 2 times w. So 2w is 216 over 432. Notice is 216 by 2 So 2 by 216, and each one of those would be squared times w squared. So we're dividing w by w squared, dividing by a fraction, multiply by the reciprocal. Okay, so we have w is equal to, we'll cancel one of the 216s. So we still have a 216 downstairs. We had 2 2's down there already, and we divided by another 2, so 2 cubed, and w to the 4th. And let's see, let's make this easier. We'll just set it to 0 and do a little factoring. So 0 is worth w to the 4th over 8 by 216 minus w. So 0 is equal to w by w cubed minus 1, and our w cubed is over 8 is 2 cubed and 216. So 216 is 6 cubed, so we have w cubed over 2 cubed by 6 cubed. So one of our zeros is happening at w equals 0, but we're talking about a width. We can discard that. Yes, having a width of 0 would minimize the size of the object in terms of surface area, but we wouldn't be able to get any material in if we have a width of 0. So we have w cubed over 12 cubed minus 1 is equal to 0. So w cubed over 12 cubed is worth 1. So w cubed is 12 cubed. So w is equal to 12. So we can go back through and find a length and a width, or we have a width. We can find a height from that and a length from that. So we can say that h is worth 432 over 12 squared. Little plug and chug on the calculator, and that is worth 3. And at the beginning we said on our constraint equation 216 is length times width times height, and just plug in what we know. So 216 is worth, we don't know the length, we know the width to be 12, we know the height to be 3. So our length is 216 over 36, and that one simplifies down to a 6. So the one other thing that we're going to do with this, you might notice we didn't use our second derivatives just yet. We're going to show that this is actually a relative min. So let me go ahead and flip over here to show that. And I'll just bring along our pertinent facts, what we have so far. So we had a width of 12, height of 3, and a length of 6. And our partial with respect to w both times was negative 864. W, that was the first derivative, my apologies. Second derivative with respect to w both times was 1728 w to the negative third. Partial with respect to 1 each was always going to be 2. And partial with respect to height both times was 432 h to the negative third. So we'll find our a, b, and c. So this is sort of our ordered triple for this. So SWW would be 1728, and W here is 12, so over 12 cubed, which is equal to a 1. So that's our A. SWH is 2 no matter what. That's our B. SHH, 432 over H cubed, so over 3 cubed, so over 27. And 432 27ths is 16. That is our C. And then you're using that table. So AC minus B squared, 2 by 16 minus 4, so 2 squared. So our AC minus B squared, if I do the substitution correctly this time, we would have a 1 by a 16 minus 2 squared. So that is 12. So that is greater than 0. A is also greater than 0. A was a 1. So this tells us this is a relative min. And that's what we were hoping. We were hoping to minimize the area. So to minimize material used, box should be width of 12 inches, height of 3 inches, and a length of 6 inches. So that gives us the optimum dimensions in order to have 216 cubic inches of storage space with the smallest possible amount of material laid out to make the box. So then our last of the word problems in this section, we're going to go back to the 2 different brands problem that we've seen in previous sections. So here, brand A, so X is in ounces, P is price of brand A per ounce, Y will be ounces of brand B, Q, price of B per ounce, so demand for A, demand for B, and our relationships. X is 100 minus 5P plus 2 times Q. Y is 50 plus 2P minus 5 times Q. And we want to know how much should the store sell to maximize revenue. So this is per ounce price. So we want to know the price of each. How much should the store, we'll say charge instead of sell to be clear. So our revenue coming in, demand of X ounces per week of brand A times P dollars per ounce plus Y ounces per week demanded of brand B times Q dollars per ounce. So then we look at cutting that down from, we have right now 4 input variables. We want to cut that down just a little bit. So a little bit of substitution. X we know to be 100 minus 5p plus 2 times q times whatever p was, and do the same thing with y. Y we know to be 50 plus 2p minus 5q times whatever we end up charging for q. So now we have r in terms of input p and q. So notice these are not subscripts. This is just saying what are my input variables. So 100p minus 5p squared plus 2pq, and distributing the q as well. So plus 50q plus 2pq minus 5q squared. And then we can do just a little sorting on that. So revenue in terms of P and Q. Let's see, we'll have a negative 5p squared and a negative 5q squared. We have a plus 2pq and a plus 2pq, so plus 4 of the pq's. And then we have 100p and 50q. So that is our revenue function. So now I'm going to ask you to find the first 2 partial derivatives. So see if you can find r sub p of pq and r sub q of pq. Okay, welcome back. So finding our first partial derivative, we have negative 10p. That term will drop out when we're differentiating with respect to p. We have a plus 4 times q and a plus 100. The 50q drops. Partial with respect to q, now the first term drops away. We have a negative 10 times q. This time the 4 and p get treated as if they're constants, so plus 4p. And 100p will drop off, and we have a plus 50. So there's our first 2 partial derivatives. We'll get our second derivatives going as well, and then we'll try to solve the system. So differentiating with respect to p twice, we would have a negative 10. With respect to p then q, we would have a 4, whether from this order or the other order. And q twice, we have a negative 10. So here, regardless of what points we find, once we figure out where each of these is worth 0, we can tell that this thing is going to be a max, a times c. So this is our a, no matter what p and q end up as. This is our b, this is our c. AC minus b squared, negative 10 times negative 10 minus 4 squared, 100 minus 16. So that is 84. That is greater than 0. A is less than 0. So this is the relative max that we expect. So now we just go to find where that relative max occurs. So we take our first derivative, set h to 0, and solve the system. So our first derivative with respect to p, setting it to 0, r sub p equals 0. So r sub p, 0 is equal to 100 minus 10p plus 4 times q. And we also have r sub q being 0. So 0 also equals, we had 50 plus 4p minus 10 times q. So let's see, both of these we can divide top and bottom, or left and right side by 2 and get smaller numbers. So I can turn this system into, let's see, 5p minus 2q is worth 50. So I move the variables to the left-hand side and cut both sides in half. Doing the same thing here, a negative 4p, a negative 2p. We'll do the simplifying as well. Negative 2p plus 5 times q is worth 25. So we're just solving the system. All right, so let's see. I'll make this guy back into the 10. So we'll do elimination on this one, since this one turned into a nice pretty linear. So we'll do 10p minus 4q is 100, and times 5 on this guy. So negative 10p plus 25q is worth 125. So 21q is worth 225. So q is 225 21st. And let's see, those are both divisible by 3. So we have 7 downstairs, and then we'll go in, let's see, 7 times, 1 left over, and 3 and 15 will go 5 times, so 75 sevenths. So q would be 10 and 5 sevenths. And finding the p, we just do a little substitution. So 5 times p minus 2 times 75 sevenths is equal to 50. So 5 times p minus 150 over 7 is worth 50 would be 350 over 7. So 5p is 350 plus 150 all over 7. So 5 times p, 500 over 7. So p is, divide both sides by 5, 100 over 7. So let's see, that'll go once, and 3 left over. 7 into 30 would go 4 times with 2 left over. Okay, so these are exact value ones. Since this is talking about a dollar amount that the store should charge per ounce, we go ahead and convert those into decimal approximations. So let's see, 100 sevenths, about, and we'll round to the nearest penny. So 14 point, we get 28, and then 5, 7, da da da. We'll round to the nearest penny. So 14.29 for brand A. So the store should charge $14.29 per ounce for P represented the price of brand A, Q represented the price for brand B. So then, let's see, 75 sevenths. We get approximately 10.7142, and it keeps going on, going on, going on. Again, we'll go to the nearest penny. So $10.71 per ounce for brand B. So that's our optimum price that'll maximize the store's revenue for selling brands A and B. All right, so that should give you enough to finish your 7-3 work. So same problems as before. If you recall, that was 9 to 33 odd, 43, 47, and 49. So you should be able to finish any of the word problems now. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.